Hello again, my lovely students. I now get to talk about college algebra topics. And this one, I get to talk about properties of logs. Logs. Because an echo was needed, obviously. So all of these properties that we're going to study are based off of the exponent rules or properties that we learned about way back in September with my horrible cheesy jokes about exponents being close enough to multiply. So in order to see how this is coming from the exponent rules, though, we have to think about it a little bit weirdly because logs themselves are exponents. So what we're going to do here is I'm going to take that log base b of x and log base b of y, and I'm going to call them something else. Now in the exponent rules properties, and in log properties, we'll sometimes use m and n as expressions. So we're going to say m is the same as log base b of x, and n is the same as log base b of y. Now, I'm going to talk a little bit differently about how this transformation works. So the book just kind of says, oh, you move this here, you move that there, and poof, you have a new equation. And it's very hand wavy, and I don't like that. So logs and exponentials are functions. Just like squaring something is a function, square rooting is a function. So these are processes that we can apply that preserve equality. So if I take the log of both sides of an equation, as long as everything's positive, that is always a caveat on logs, just like with square roots, everything has to be positive, then the resulting equation is also equivalent. Likewise, if I apply an exponential to both sides of an equation, the result is also equivalent. So the way that looks, though, is a little weird. But exponentials and logarithms are inverses of each other. They are designed, actually, to cancel each other out. Specifically, logs were designed to cancel out exponentials. The idea that there had to be something, so this is what we decided to call it. So to cancel out log base b of a thing, we need to use base b as an exponential. The way I write it is like this. I put b with a caret on both sides. This is very, very much why I'm using a different color. So on the left side, I had m, now I have b to the m. So I'm just going to write that like a normal looking b to the m. Now over here, b to the log base b of x, well, b and log base b cancel each other out, just like squared and square root. So those two undo each other, and all we have left is what was inside the logarithm, which is x in this case. Then likewise over here, we're going to do the same process. It's still base b, so we are going to use the b exponential on both sides. Now when we do this, just like when we square both sides, you don't get to break the square across addition or subtraction. So here, if there's a whole bunch of terms being added or subtracted, you're doing the exponential to the whole thing. So we're going to have other ways to kind of compress and expand stuff when we want to use those properties. But how these work as a function is a little bit different thinking, but I find is a lot more useful because this is how you can actually use logs and exponentials. This is their whole purpose in life. All right, so now we have b to the n equals, and again, we get that undo of each other, gone, and just y. All right. So now I want to know, so I have what x is and I have what y is. And if I look, well, it's a little bit different, but now we're going to look at the product of those two. All right, so xy is the same as b to the m, b to the n. But we can really just write that as b to the m plus n. There's our exponent rule. Side by side, those exponents add. Now that I have that, I don't want them as exponents. I want them on the line because that's where stuff is with logarithms. Exponents are no longer hiding up top where we can't get to them. Logarithms bring them down to the regular line so we can break them apart and move them around as we want. So that is what we're going to do now. And again, it's going to look a little weird. And magic of the internet, or magic of the surface at least. So like before we applied the exponential to both sides, now I'm going to apply the logarithm to both sides. So I'm going to take the log base b of everything on the left and the log base b of everything on the right. It's two big things. So just like I would square root both entire sides, I do have that caveat, everything inside has to be positive, same here. Can't have any negatives, but the book will they'll write it for a while and then they'll hand wave it and be like, and all the logs after this are positive. Until you get to the equations, then it's not hand waved anymore. It's annoying, but that's next week's problem. All right, so log base b of x, y, and that's actually the first part of the property. If we scroll it a little, see? Now over here, log base b of b to the m plus n. Log base b and b cancel each other out. So this is now log base b of xy is the same as m plus n. But I know what m and n are. Those were my pink equations back up here. So this must mean that log base b of xy is the same as log base b of x plus log base b of y. So we have proven the rule. Yes, I know it was long and a pain in the butt. So overall, the idea is because our exponent rules when stuff was side by side, we could add the exponents. So if the logs are being added, we can compress it into one log or one exponent where the things are, it's not exponents then, this is why it's kind of weird. But side by side, we have a sum, smushed together, it's a product. So sometimes I kind of think of it as like a step down, like multiplication versus addition. And then we're going to see in a minute division and subtraction go together. All right, so here we have write the logarithm as a sum and simplify if possible. Assume that all variables represent positive real numbers. Yay! So that just means we don't have to worry about the, oh, make sure the inside's positive. All right, so some of these are going to simplify, others we just expand it and we're done. But that's what I call these when it says write it as a sum, or later it's going to say a sum or difference. That's taking one log with an ugly mess and stringing it all out into a whole bunch of logs, but what's inside the log is actually more simple, sort of. But then you have a bunch of logs instead. There's times in calculus where you want one form versus the other form, and it can make what was a disgusting calculus problem into a, oh, that's way easier problem. Because it turns out natural logs have the like special derivative. All right. So log base 4 of 16 times x. So we are going to write two logs. They have to be the same logs, base 4 in this case. So we have log base 4 of 16 plus log base 4 of x. I have no clue what x is besides that it's positive, so I have no way to calculate log base 4 of x. But log base 4 of 16, that I can do something with. So this is where I kind of break it down and think, all right, what do I know about 16 in relation to 4? I do know 16 is 2 to the 4th, wrong 4, with 4 as the base, what is 16? So 4 squared. I could write 2 to the 4th there, but we would end up having to use different kind of log properties to finish it out. So here, if I write it in terms of the base the log is in, then I'm using that same log base b of b to the property where those guys cancel each other out. And this is just going to be that exponent 2. It still has the log base 4 of x added on there. So that's what they mean by simplifying. One of the logarithms may actually be calculable. And so you're responsible for simplifying it down. If it calculates into a decimal, you are not responsible for it. They don't want you to do ugly decimals. They just want, if it works out to like a pretty fraction or integer, that's what they want. All right. So now we have the natural log of 12xy. Little bit different. Before it was just 16x. Now it's 12x and y. Well, let's see what happens then. So some people might look at this and think of it as 12x times y. So I'm going to go with that. So our lovely mess here is the same as the natural log of 12x plus the natural log of y. I write my natural logs as capital L and then lowercase n, because when I try doing curly L's or lowercase L's, it ends up looking like 1n and people get confused. So I would highly recommend, like, however you're going to do ln, just make sure you always know that thing you write is ln and not something else. So in my own notes, a lot of times I would write it in cursive. And yeah, sometimes it would be an M instead of an N. So just keep that in mind. All right. So natural log of y, I can't simplify that any, but it is a log on its own. Now 12x, though, we know is 12 times x. So I can apply the log property again. So this is now the natural log of 12 plus the natural log of x plus the natural log of y. So repeated products, I just get repeated additions. So it doesn't matter how many things I'd multiplied up there, everybody would get a log. And in calculus, things that are being added are way nicer to take the derivative of than things that are being multiplied. That is the power of this, or one of the powers of it. Now, the natural log of 12, I could crunch that on the calculator, but the natural log of 12 in math terms is more precise than the decimal you would get from the calculator. Even though the decimal has more meaning, that's just how mathematicians see it. The natural log of 12 is a precise thing, and the decimal is only a close approximation. And again, I present my theory that mathematicians never had to take any sort of applied chemistry. All right. So now the log of 100x. All right, well, I got my rule. Log 100 plus log x. Now here's one of the nice things. Since that's just regular log, there's no extra little base. That's the same as the log on your calculator. So you can right here, if you're not sure if that simplifies, crunch it on the calculator and see what you get. And in this case, you get an integer. It's not an ugly decimal. And the reason it's an integer is you have to remember log is really log base 10. So how do I write 100 in terms of 10? And it is 10 squared. So log base 10 of 10 to the all cancels out, and we just get 2 on the line. All right. So there's how those three shake out. I'm going to cut this here, and then I will talk about the quotient property in the next one.